Welcome to Algebra Review with Dr. Gallenstein. My objective with this video and this exercise is just to give us some practice with solving a maximization problem where I'm going to take my time through all the algebra. I'm going to go step by step through all the algebra, and I'm going to solve it out in black. But then every time I have some algebra rule that I use or some algebra trick, I'm going to pause. I'm going to write down what that rule is in blue. So we're going to practice solving a problem, solving a maximization problem. And as we go through it, we're going to have a nice algebra review. Afterwards, we can summarize some of the algebra tools that we use during the exercise. Okay, so I have a maximization problem where my objective function is x to the alpha times y to 1 minus alpha. In this objective function, there's two variables, x and y, and then there's one parameter, alpha. This is a Cobb-Douglas function, which will encounter Cobb-Douglas utility functions and Cobb-Douglas production functions. So this is a common function. You'll see something like this. Subject to the constraint that z equals beta x plus theta y. So we just have some, we have our variables there, x and y, and we have a couple more parameters, z, beta, and theta. I am going to use an example that has a lot of parameters because it'll give us more opportunity to practice with our algebra, and it's to use somewhat of a more complicated exercise for our illustration. So hopefully we'll get a lot of value out of this exercise. So when we do a maximization, the first thing that we're going to do is set up our Lagrangian function. So I'm going to set up my Lagrangian function for this equation. So Lagrangian is a function of the variables. Okay. And it equals the objective function plus this variable lambda, which we know from our economic thinking, lambda is the shadow price. And then we have our constraint. Okay. So the first thing we do is we set up a Lagrangian function. And then we're going to take the first order conditions. The first order conditions, which we might call FOCs, the first order conditions are the derivative of the Lagrangian function with respect to each of the variables. And then we set those derivatives equal to 0 because we know that a function is at its maximum, or it's at an optimal point, but if the function's concave, it's at its maximum, at the point at which the derivative is equal to 0. So that's the intuition. So our first order condition is the derivative of L with respect to x. And so I'm going to take a derivative of this entire function with respect to x. Okay, well, let me go through every step. What I'm going to do is I'm going to first rewrite this function in a way that's a little bit more clear. And I think anytime I'm going to do an additional step or an extra step, I might use red. So let me write this out just in a way that might make it a little bit more clear. I'm going to distribute lambda. Distribute means that if I have lambda times, so parentheses, times the series of terms, so addition, within the parentheses, I can quote-unquote distribute the lambda over the addition. So what does that mean? That means that this term here is the same thing as lambda z minus lambda beta x plus lambda, or minus lambda theta y. And I just realized that I have a typo. I guess it's not a typo because I'm not typing. It's a right-o, perhaps. Okay, but I wrote this wrong. This is a minus and this is a minus, so excuse me for that. Okay, so I can distribute the lambda across these terms. That's a general rule of algebra. So I'm going to write a general rule here in blue. If I have some variable a and it's multiplied by b plus c, that is equal to ab plus ac. It's a general rule of algebra, is that multiplication distributes across addition. So first general rule. Okay, so now I've simplified this and I can take the derivative. Okay, so I'm going to take the derivative with respect to x. Now when I do that, what I'll do is I'm going to go through every term, and when I say term, I mean some independent quantity that is distinguished from usually plus or minus. So this is a term, this is a term, this is a term, and this is a term. So I'm going to go through each term, and I'm going to take the derivative of each term with respect to x. So let's start here. I have x to the alpha times y to the 1 minus alpha. I'm going to take the derivative of this with respect to x. This is a little bit of a messy function. So let me just review what a derivative looks like. So if I have some variable x and it's raised to some power b and it's multiplied by some parameter a, then the derivative, so let's say this is f of x equals that. The derivative of f of x with respect to x is equal to b a x to b minus 1. Sorry, I'm running out of space there. Okay. So I look at this and I think, all right, this y to the 1 minus alpha is kind of like my a. I can treat this like the a in my formula, and this alpha, I can treat it like the b in my formula. In fact, I might even rewrite it to make that more obvious. So let me rewrite this to make it more obvious. I've just rewritten this. All I've done is I've taken the y to the 1 minus alpha and I put it in front just so that it looks a little bit more like this. And I put a parenthesis around it just so it looks more like this. So these are the same this is the same thing as this, but it's a little bit more obvious. When I write it that way, I think, oh, okay, the y to the 1 minus alpha is just like a, and the alpha is just like b, which means my derivative is going to look like this. Y to the 1 minus alpha times alpha times x to the alpha minus 1. That will be my derivative for this term. Now, let's go to the next term. Lambda z. There's no x in lambda z. What is the derivative of basically just a constant? So let's take a look at that. Lambda z, looking at this, there's no x here. That means lambda z is kind of like lambda z times x to the 0, because x to the 0 equals 1. So this is the same as this. So I look at this and I think, okay, let me apply my rule. The lambda z is like my a. Okay. The 0 is like my b. And so if I take the derivative of this, what I see is that I take 0 times this, right? Because I bring the b down, multiply everything by b. So it would be b a. So what it would be, let me write it over here. If I take the derivative of lambda z x to the 0, what that would be is 0 times lambda z x to the 0 minus 1. But we look at that and we realize, wait, 0 times anything is just 0. So the derivative of lambda z is just 0. Okay, so let's go on to the next term. Lambda beta times x. Okay, there's an x in this. I can take the derivative of this. All right, I don't need to simplify it. All I need to notice is that lambda b is just like my a, and x is raised to the 1 power. So b here is 1. So then my derivative is 1 times lambda beta times x to the 0, and x to the 0 is just 1. And so the derivative of this is minus lambda beta. Okay? And now we're going to come to this last term. We look at the last term, and it has no x in it. So for the same reason that this is equal to 0, this is the derivative of this is 0. And so we're done. The derivative of the equation is just this, equals 0. Okay, let's go to the next one. The second first order condition. The derivative of L with respect to y. So now I'm going to look at this term again, and I want to take the derivative with respect to y. So that means now I'm not looking at x anymore, I'm looking at y. When I look at this, I think, okay, this x to the alpha is kind of like the a before, the y is like my x before, and the 1 minus alpha is like b. And so then I use this equation, I use this formula for taking a derivative, and what I find is that I have 1 minus alpha times x to the alpha times y to the 1 minus alpha minus 1. So the 1's cancel out and you get minus alpha. Okay, so I got the minus alpha because I took the 1 minus alpha, subtract 1, so then the 1's cancel out and you just get minus alpha. Okay, so now let's go to the next term. Lambda z. Does lambda z have y in it? No. So the derivative is 0. All right, next term. I have minus lambda beta x. Does this term have a y in it? No. So the derivative is 0. All right, next term. Lambda theta y. Does this have a y? Yes. Okay, well, let's take a derivative of it. We'll notice that the lambda theta is just like my a, y is just like x, and b must be 1. So I take the derivative and I find that the derivative is lambda theta. Okay, set that equal to 0 because it's the first order condition. Done. All right, next. Third first order condition, the derivative of L with respect to lambda. So there's two ways we can look at this. First, we could look at the original equation, and we could just treat this entire term, if you will, within the parentheses. We can just treat that like a. We'd say lambda is raised to the 1 power, so the derivative is just z minus beta x minus theta y. Or I can use this where it's been distributed, the lambda's been distributed. So let's use this one, and then I'll kind of show, I'll show the intuition for the other one. Okay, so let's go term by term. Does this have lambda? No. Okay, derivative 0. Does this have lambda? Yes. Derivative must be then be z. Does this have lambda? Yes. The derivative? Beta x. Does this have lambda? Yes. Derivative? Theta y. All right, equals 0. Now I look at this and I realize that this is exactly what's inside of the parentheses. So I could have skipped a step and I could have just said that this whole that the derivative of this whole term is actually just equal to the z minus beta x minus theta y, because this whole term here is multiplied by lambda. So I could just have thought about this as being the a in my derivative equation. But we can find it either way, whichever one you find easiest. Okay, so here we have our first order conditions. Now we need to solve these first order conditions for x, y, and lambda. This is not always an easy task. And when you have a complicated objective function, it can be even more difficult because we're going to have to use some different algebra tricks. So let's come down here and start doing that. Now I happen to know that there's usually two good approaches for solving these kinds of problems. One approach is that you solve the first order condition for x, the second first order condition for y, and you'll get functions of a function of x, or you have x as a function of lambda, y as a function of lambda, and then you plug those in here. I've illustrated this in class. That's one technique. Another technique that you can do is you can solve these equations for lambda and set them equal to each other. That's what I'll use in this example. So what I'm going to do is that I'm going to solve the first order condition for lambda. Now let me just pause for one moment. I want to be clear about where we're going. What's our objective? We want to isolate x and isolate y and isolate lambda. What we want is this. We want x as a function of the parameters. That means x should equal something that only has parameters in it. It means it only has alpha, beta, theta, and z. It only has the parameters. That's what I want. Parameters and then numbers, but no variables. It doesn't have, so I want to find a value of x that equals some term that is only composed of numbers and then the parameters. That's what we're looking for. Once we have that, we can say that it's the optimal x. We can say that we've solved for it. So that's the objective. This is what I'm looking for. Okay, so then let's set out to do that. I'm going to use the technique where I'm going to solve for lambda. So let me solve for lambda. Let's solve this for lambda. I'm just going to rewrite it. Okay, I'm just going to rewrite this term a little. We're going to bring the alpha out front. It's just a little bit cleaner. It looks a little nicer. Minus lambda beta equals 0. So let me solve this for lambda. I'm going to go step by step. The first thing that I can do is I can take. So when I mean solve for it, I mean I want to isolate it. I want to get it alone. So let me try to manipulate this to get it alone. So one thing I'm going to first do is, let's say I'm going to take 1 minus alpha, or minus alpha beta equals, and I'm going to take this whole term to the other side. I can always do that. What I'm effectively saying is that I can subtract both sides of an equation by the same number. Or I can say that I can take something to the other side as long as it's a minus. So I can do this. This is good algebra. I can bring this to the other side and make it a negative. Let me illustrate the algebra principle here. If I have a plus b equals 0, I can subtract a from both sides. I can subtract any number from two sides of an equation, and that's okay. So let me just illustrate that. I have a plus b. I'm going to subtract a from both sides. So then I get this. But I recognize that a minus a equals 0, and so then this would equal a equals b equals minus a. which is the same thing as basically just taking the a, moving it to the other side, and adding a negative sign. So this is kind of a nice little trick. Okay, so that's the first thing I do. The next thing that I'm going to do is I'm going to divide both sides of this equation by lambda. In fact, negative lambda. So let me illustrate that. I'm going to divide both sides by negative lambda. Oh, pardon me. I'm going to divide both sides by negative beta. Beta is what I'm looking for. I'm sorry, lambda is what I'm looking for, so that means I want to divide both sides by beta. All right, pardon me for that. All right. Okay. So now I'm going to divide both sides by beta. I can do that. Let me illustrate the principle. If I have, let's say, A equals B, this is the same thing as A over C equals B over C. I can divide both sides of an equation by the same number. That's okay. That's algebra. I can always do that. I can divide both sides of an equation by a number. All right, so this is totally safe for me. I can divide both sides by beta. When I do that, I can cancel out the betas on this side, the negative betas, and get just lambda. So I have lambda on this side equals this term here. Okay. Negative beta. Now at this step, I'm going to recognize that the negative of a function can be also written as something else. Let me write it a little bit differently to illustrate. I can say this is negative 1 times alpha y x alpha minus 1 over negative 1 times beta. And so when I'm here, I can recognize that these negative ones cancel out. So after the negative ones cancel out, I get lambda equals alpha y 1 minus, alpha y to the 1 minus alpha, x to the alpha minus 1 over beta. So there we go. I have one expression for lambda. It's as a function of x, of y and x. All right, so I've just solved my first order condition for lambda. I'm going to do the same thing for the second first order condition. So I'm going to move this over here. Sorry, it's a little bit off screen. I'll bring it back on screen as needed. So here we have the second first order condition. Let's solve this for lambda. So I'm going to rewrite it. 1 minus alpha x alpha y minus alpha minus lambda times theta equals 0. So let's solve this for lambda. So we're going to move quickly through this because we've just illustrated the relevant techniques, so we can just do this really quickly. Okay, we're going to divide both sides by negative theta. I'm going to skip some steps because we know how this works from what we just did, and we're going to get 1 minus alpha x to the alpha y to the minus alpha over theta. Okay, now at this point we have two equations for lambda. We have the first one that we calculated a moment ago. We've got a second one. Both of these expressions equal lambda, so I can take advantage of that to try to solve for x or y. So I'm going to do that. I'm going to write alpha y to the 1 minus alpha, x to the alpha minus 1 over beta equals 1 minus alpha, x to the alpha, y to the minus alpha over theta. Okay, these equal each other because lambda equals this and lambda equals this, which means this equals this. these two equal each other. So I'm just going to rewrite those. So I have that here. So these two terms equal each other. All right, now I have an equation that is only a function of y and x. I'm going to try to solve this for x. Now you look at this thing and you're thinking, how in the heck are you going to solve this for x? This is nuts. This thing is complicated. There's fractions. There's exponents. This thing is a mess. How are we going to solve this? Actually, we can use algebra tricks to solve this. And it's really sneaky, but we're gonna do it. Okay. First thing we're gonna do is I wanna get rid of these fractions. One way I can get rid of fractions is by using one of my rules of algebra. So let me illustrate. If I have a equals b, I can multiply both sides of that equation by the same thing, and it'll still be equal to each other. So I can multiply both sides by c. Let's say I do that. I multiply both sides by c, and it's still equal to each other. That means I can multiply both sides of an equation by the same number and maintain the equality. So this is a rule. But let's use that rule. I'm going to multiply both sides of this equation by theta. So let's multiply both sides of the equation by theta. And let's multiply both sides of the equation by beta. Both sides of the equation times beta. We do that, and we think, look, betas cancel out here, thetas cancel out here, so what we get is theta alpha y, 1 minus alpha, x alpha minus 1 equals, the thetas cancel out here, so beta 1 minus alpha, x to the alpha, y minus alpha. Okay, we've solved one of our problems. We've gotten rid of the denominator. Now let's try to think about how we can start isolating x and y. Now this one's really tricky. So let me show you what we're going to do, and then I'll explain some of the algebra behind it. What I'm going to do here is that I'm going to divide both sides of this equation by x to, let's say, x to the alpha minus 1. I'll show you why I do that in just a minute. I'm going to divide both sides by x to the alpha minus 1. If I do that, I see that these two terms cancel out, okay? So we're able to get rid of these complicated x terms over here, but then we're stuck with something very interesting here. We have x to the alpha over top of x to the alpha minus 1. This is tricky. So let me just write this over here. Let me write this separately. X to the alpha over x to the alpha minus 1. If we use our algebra tricks, we can realize that, oh, look at that. I can actually simplify this quite dramatically. Let me illustrate the algebra trick. If I have a to the b divided by a to the c, this is the same as a to the b minus c. Now this is a really helpful trick. So let's apply that here. This is equal to x to the alpha minus 1, where we say that alpha is b and alpha minus 1 is c. So this is this is x raised to the alpha minus 1. If we simplify this equals x. Why is that? Well, it's because we have alpha minus alpha, which is 0. And then we distribute, so if we distribute this negative sign, I'm going to write this separately just to make this clear. I've got alpha minus 1. This is the same thing as alpha minus alpha plus 1 because I've distributed the negative sign, which is equal to 1. Okay, so then x to the alpha over x to the alpha minus 1 is actually just equal to x. So when I look at this, this looks really, really complicated, but it's actually, we can actually simplify it a lot. So let me rewrite this with the simplification. Right now I have theta alpha y to the 1 minus alpha equals beta 1 minus alpha times x to the y minus alpha. So doing this, I have substantially simplified this problem. I just got rid of the exponent. I had, up here, I had a really, really complicated function where x and y are both raised to exponents, and there's fractions. So first I get rid of the fractions, and now I'm going to get rid of those exponents by using my algebra tricks. Let me do this again. This time, let me divide both sides by y to the minus alpha. Okay, I do that, and once again, I see, hey, these cancel out. So that's nice. These cancel out. And then I'm over here. I have the same situation I had before. So let me write that over to the side. I have the situation where I have y to the 1 minus alpha divided by 1 to the minus alpha. This is equal to y, 1 minus alpha minus negative alpha, which is equal to y to the 1 minus alpha plus alpha, which is equal to y. So there we go. Again, we can very much simplify this. So let me apply the simplification. We have theta alpha y equals beta 1 minus alpha x. So that was a major simplification. We have gotten rid of the fraction, and we got rid of the exponents for x and y. This is a much more manageable equation. And the only way we were able to do it is by utilizing some of these algebra tricks. Okay. And let me pause just a second to make sure that this canceling out operation makes sense. So another algebra tool. If I have a times b divided by b, this is equal to a, because we can say that the b's cancel out. So hopefully that is helpful. Okay, so here we go. We have this equation, and this is a much simpler equation. We can solve this much more directly. So let's just solve this. We can solve it for y, or we can solve it for x. Either one's fine. I'm just going to solve it for y. y